right, class, next I want to talk about normal probability distributions. This is all of chapter 6, and this is one of the most important things we're going to cover in this course. It's truly the most applicable. So let's look at this. So here's a histogram for a distribution of 300 natural births, right? The left axis shows the number of births for each 4-day bin. This shape right here is called our normal curve. It's also called the bell curve. So the normal distribution is a symmetric bell-shaped distribution with a single peak. And the peak is the mean, median, and mode of the distribution, right? If all of these are equal, we have a symmetric, non-skewed distribution. Its variation can be calculated by the standard deviation of our distribution. And that's represented by a sigma. So let's take a look at both these graphs. Are they normal? Well, they're both symmetric. They both have a bell shape. The only difference is one has a larger standard deviation, so its values are more spread out, and the other one has a smaller standard deviation, so its values are more concentrated, closer to the mean median mode. The area that lies under the normal distribution curve, corresponding to a range of values on the horizontal axis, is the relative frequency of those values, right? Relative frequency being a decimal, being kind of a probability. Friendly reminder that the area under the normal curve is 1. And because the total relative frequency equals 1, it makes sense that the area under our normal curve must equal 1, right? This is a type of probability distribution. This is the most important thing I need you to remember, okay? So let's talk about some conditions for a normal distribution. So a data set that satisfies the following 4 criteria is likely to have a normal distribution. So data values are clustered near the mean, which is the same as the median and the mode in this case. Data values are spread evenly around the mean, making the distribution symmetric. Larger deviations from the mean become increasingly rare, right? Producing these tapered tails of our distribution, right? And the individual data sets result from a combination of many different factors, such as genetic and environmental factors. So this is data that typically occurs naturally. So which of the following would we expect to have a normal or a nearly normal distribution? Scores on a very easy test. Well, here's my test. Scores go from 1 to 10. If it's really easy, we would suspect most people that get a really good score, right? Is this a normal distribution? No, it is skewed to the left. How about tree lengths in a forest? Yeah, that makes sense. That's something that occurs naturally. This would definitely be normal. How about, foot lengths of a random sample of adult women, right? That's a genetic factor. Women occur naturally. This is also normal. How about luggage weights on an airplane? I think it depends on how you pack. I'm a get as close to 50 pounds as possible, sometimes go over the limit person. So this would be not normal. What about the temperature in an oven that's not been turned on or open all day? So we're just taking the temperature of a bunch of ovens. I think this would be nearly normal, if not normal. So pulse rates of randomly selected males have a distribution with a mean of 70 beats per minute. We use mu, right, to denote mean. And a standard deviation of 11 beats per minute. Could we consider this a normal distribution? Well, yeah. Pulse rates is a naturally occurring factor. So let's go ahead and draw this normal distribution. So here I have my normal curve. My mean is 70. My standard deviation is 11. What's interesting, though, is here I have the pulse rates of males, right? Again, sigma. And here I have, if I was to go 1 standard deviation above the mean, I would have 81. If I was to go 2 standard deviations above the mean, I would have 92. And remember, anything above 2 or below 2 standard deviations from the mean is unlikely to occur. And I also want to go out 3 standard deviations. This is a good habit to get into. Now, why do I want to do this? Well, we know something really important about the first, second, and third standard deviations away from the mean. So we have a 68, 95, 99.7 rule. What this means is that about 68% of the data falls within the first standard deviation. So because this relates to percentages, the area in this dark green section is 0.68. What it also tells me is that 95% of data lies within the first 2 standard deviations. So the area under this portion of the curve has an area of 0.95. And that 99.7% of data falls within the first 3 standard deviations above and below the mean. So this part has an area of 0.997, and the total area under the normal curve is 1. So we are going to be able to use this normal, this 68, 95, 99.7 rule for normal distributions to make some calculations. So again, here's a little breakdown of the rule. So the tests that make up the verbal and mathematics SAT are designed so the scores are normally distributed with a mean of 500 and a standard deviation of sigma. Let's go ahead and interpret this statement using percentages. The first thing I want to do, a good habit to get into, is to draw my normal distribution. I have a mean of 500. I want to go 3 standard deviations above and 3 standard deviations below. So if I go up 1 standard deviation, I'm at 600. 700 would be 2 standard deviations. 800 would be 3 standard deviations. I want to do the same thing below the mean. If I go down 1 standard deviation, I'm at 400. 2 standard deviations, I'm at 300. And 3 standard deviations, I'm at 200. So let's interpret this statement using percentages. So I could say that 68% of students score between our first 2 standard deviation holds 0.68, so 68% of data score between 400 and 600. I can also do the same thing for our second standard deviation. 95% of students score between 300 and 700. Last but not least, if I go 3 standard deviations out, 99.7% of students score between 200 and 800. Vending machines in the U.S. Can be adjusted to reject coins above and below certain weights. So the weight of legal U.S. quarters has a normal distribution with a mean of 5.67 grams and a standard deviation of 0.07 grams. If a vending machine is adjusted to reject quarters that weigh more than 5.81 or less than 5.53 grams, what percentage of legal quarters will be rejected by the machine? The first thing we're going to want to do is draw our normal distribution. So I've got a mean of 5.67. If I go up 1 standard deviation, I'm at 5.74. Up 2 puts me at 5.81. Up 3 puts me at 5.88. So plus 1, plus 2, plus 3. I need to do the same thing below the mean. If I go 1 standard deviation below the mean, that puts me at 5.60. If I go 2 standard deviations below the mean, that puts me at 5.53. And if I go 3 standard deviations below the mean, that puts me at 5.46. So, if a vending machine is used to adjust quarters that weigh more than 5.81 or less than 5.53, what percentage of legal quarters will be rejected? Well, 5.81 and 5.53 between those two, there's 95% of data, so the area here is 0.95. And I want to know, it's going to reject quarters that weigh more than 5.81 or less than 5.81. So I need to know the area in those two tails. Sometimes we call these area tails. Well, I know that the total area under the normal distribution is 1. So if I take 1 minus 0.95, I'm left with 0.05. So 5% of legal quarters will be rejected by the machine. So let's go ahead and look at another example. So we can apply the 6895-99.7 rule to determine when data lies 1, 2, or 3 standard deviations from the mean. Assume 1,000 students take an exam and the scores are normally distributed with a mean of 75 and a standard deviation of 7. Let's construct our normal distribution and label our percentages as well. So I know my mean is 75. I want to go 1, 2, 3 standard deviations above the mean, and 1, 2, 3 standard deviations below the mean. If I go up 1 standard deviation, that puts me at 82. If I go up 2 standard deviations, that puts me at 89. And if I go up 3 standard deviations, that puts me at 95. And then my notes blow away because I'm recording on my porch. Okay. Ooh. Now, what if I go standard deviations below the mean? If I go 1 standard deviation below the mean, that puts me at 68. If I go 68. If I go 2 standard deviations below the mean, 61. If I go 3 standard deviations below the mean, I'm at 54. So this asks us to label our percentages. I don't need to interpret using a sentence like we did in a few examples ago. Let's label our percentages. So if I go within the first standard deviation, I have 68% of data. If I go within the second standard deviation, I have 95% of data. And if I go within the third standard deviation, sorry, I couldn't pick a color, I have 99.7% of data.